Good evening, everybody who's with us this afternoon, and those of you watching on our YouTube channel at a later stage. This is the first time we've done a presentation for young scientists, so we'll see how it goes. This afternoon is all about muons. Now, those of you in the room, and I can see on the camera as well, we've got two detectors set up, and they are flashing. And don't say anything now, but there's something quite interesting about the flashes, and we'll come back to that a little later, okay? Right, moving on. The content of this presentation is based on a talk I gave at the European conference on radio astronomy, and this has been rejigged for the younger scientist because we need a bit of background information on particle physics. Otherwise, as we move forward, it isn't going to make a great deal of sense. Okay, right. We're going to look at muon detectors. We're going to see how muons are made, and most importantly, why are we doing all of this? Why are we doing it? Okay, now to get started, we must understand atoms. And the question is, what is an atom? If you've got any idea, Hannah was first, but she's also one of the oldest. I'm going to take Bethany. What is an atom, Bethany?
A very, very small thing.
A very, very small thing. I'm going to take William and then come to Hannah. William.
It contains protons, neutrons, and electrons, and it makes up everything.
You can come and sit here because have you been peeking at my slides? Hannah, what were you going to say?
I was going to say basically the same, but there's like a nucleus inside of an atom.
No, that's the same.
And then in the nucleus, which is in the atom, there's neutrons and what's the other one? I can't remember, but around the nucleus,
Yes.
there's electron shells.
Yes. Okay, that is most excellent. William, what were you going to add to that?
You forgot a question mark on the end of what is an atom.
Yeah, there'd be loads of grammatical oddities in this presentation. Right, in the middle, neutrons and protons, which is exactly what we've said. And spinning around, there are electrons, okay? Now, if you didn't know that, and there may be people here that didn't know that because it's quite advanced, put your hand up. Excellent. Right. At the end, I'm going to ask, what have you learned that you didn't know before? Okay? So, now then, how big is an atom? And I've put a pinhead there. And can we just see, just to get the scale of atoms, how many atoms can we get across the top of a pinhead? Any idea? Bethany?
A billion.
A billion. Okay. William?
A lot more than what Bethany said.
More than a billion. Okay. 10 million.
That's close.
10 million across the head of a pin. Okay. Well, they are small, and 10 million is quite a big number. Right, so very small. Now, where do muons come from?
Space.
Yes, the answer is space. They come from space. Okay, now then, this is a very interesting story, and we're going to come back to this a little later. Right, the universe can make stars, and stars can explode. Hang on. An exploding star is called a... Okay, great. This one, and this was in it's September time, October last year, this star exploded and made a black hole. And a huge amount of energy was released. It was incredibly energetic. And we're going to come back to this story later, okay, because it's quite interesting for our discussion this afternoon. Okay, so they come from outer space, they come from inner space as well. So they can come from the sun. Yes, muons have a massive energy, 4,000 million batteries worth. Matthew.
You said outer space and inner space. What's the difference?
Okay, outer space is outside of our solar system. And then what I just said as inner space is from within the solar system, and they come from the sun. Now this diagram is not that easy to understand initially, but this is planet Earth, and this is the sun. And the sun, we think it just sits up in the sky shining brightly, but in fact it's periodically squirting masses of energy at us. In fact, all around and away from us, towards Earth. And the energy comes from the sun in the form of many different things, but protons, radio waves, X-rays, light. And what we are interested in this afternoon, because William and Hannah already noted that in the middle of atoms there are protons. Protons can lose their electrons, and so they just hang around all on their own from hydrogen, mainly hydrogen or helium atoms. And so there's just a proton. And these have massive energy. They get squirted from the sun periodically in like lumps. Maybe a day or two will go by and there'll be nothing, and then a whole lot will come together like a red bus. William?
Where are the neutrons then? Because if the proton's in the middle, then the electrons are circling around.
Yeah,
not the neutrons.
that is a really good question, and it's another story. And the neutrons form a part of the solar wind, and it's another set of experiments that we can do. But that's not what we're going to discuss this afternoon. But people do look at free neutrons, and they can get down to ground level. Okay, so the Earth is like a big magnet, and the protons can get accelerated towards the Earth. Okay, some don't, but some do, and that then takes us on to another part of our story this afternoon. Okay. Wow. Oh yeah. Wow. I put that in. Okay. One interesting thing about muons, and this is a great example for any of you that will be doing physics A level, because it's actually a part of the syllabus. But muons suffer what Einstein would call time dilation. Okay. Basically, because they have such a huge amount of energy, how many batteries?
4,000.
Yes. They travel, for the purposes of our discussion this afternoon, at the speed of light, which is very, very fast indeed. Okay? If you're studying physics, then they travel at 99.9999% of the speed of light. Okay? And that difference is important if you want to do other stuff. But for us, they travel at the speed of light. They're very energetic, and they are very small. Okay, now then a little bit of atmospheric physics here. Again, it adds into our story. So, Bethany.
What's that?
I'm just about to tell you. That's the sky, and free protons get accelerated into the upper atmosphere. And there's one, look, do you see it? Oh, it's gone. There it is. So this is a proton coming into the upper atmosphere. And the proton, it has a lot of energy, and it starts to break up into the things that make protons. And we won't go into all of this, but there's p ions, k ions, and then neutrons.
Basically, a bunch of really, really tiny things.
Yeah, even tinier things. And William mentioned neutrons. Are they coming in separately? Neutrinos, you may have heard of neutrinos. They're a part of this process. And for us this afternoon, muons are coming in. And then there's one muon every square centimetre every minute at sea level. And these things are very energetic, and they can go right through your body, out the other side, and into the Earth. And they go several several tens of meters, hundreds of meters into the ground before they lose all their energy. Nessie first.
Does it hurt?
No, can you feel them? While you've been sitting there, probably about 50 have gone right through your body and out the other side. Hannah?
Does it go in between the atoms that make up your body?
Yeah, it will do. Bethany?
How many have gone through my body?
It'd be about the same, because if you're a muon, then you're about the same size as Bethany.
I'm sitting higher than her.
Yeah, that's very good. And the height is a very interesting point that will go into our story a bit later on. And then just for completeness, the muon itself breaks up into electron, muon neutrino, and an electron antineutrino. But that is not for this afternoon. When you go to university and study physics, then this will become very important and you'll remember this, okay? Now, a muon detector, and we've got two sitting here, will detect muons and other stuff. Bethany?
My dad told me that like 15 seconds ago. And also, is there a muon going through me right now?
Well, maybe, maybe not.
Could be it.
Yeah, there's one. Did you feel it? Didn't you? Okay, Hannah, what were you going to say?
Is it every time it flashes there is a muon?
Ah, interesting. We'll come back to that question in just a second. William?
What's the other stuff?
What's the other stuff?
Okay, I will explain that, and we just take Noah's question.
Isn't it when both the flash and the muon?
Yes. Okay, other stuff will be beta radiation and gamma radiation, and
The Hulk.
the Hulk. Those species of radiation are with us all the time. They come from the geology. They come from building materials. They can come out of the ground. But we're not interested in that stuff. We're only interested in muons. Yeah, how can we tell a muon from other stuff? Two detectors. So Noah was paying attention. And these are just a pair. We've got two set up here. And have you noticed anything about the way the lights flash? They flash quickly. Every flash is an event. The top one flashes only when some radiation, in this instance muons, goes through both detectors at exactly the same time. The other stuff, the other radiation, is just random and may not, and probably not, be coincident with a muon. And so we run them in coincidence mode, and then we can eliminate other stuff. Hannah?
Can you buy them in pairs or can you get one like separate?
Yes, you can buy them in pairs, and you can buy them individually. Hannah, Lisa, Mary.
What's the actual detector bit?
Oh, that's the next slide, I think. If it's not. Yeah, a muon is so strong, it's seen on two detectors at the same time. Other stuff is just random. Bethany.
Does it have something to do with the height?
It has something to do with the height, and we'll come to that in a minute. You're jumping ahead about 6 slides.
Does the detector have something to do with that?
Does it have to be one on top of the other?
Yes. It has to be on top of the other, but
It couldn't be next to each other, it has to be on
if they were next to each other, a muon would have to go through them at this angle,
Yeah.
and the distribution with angle isn't it's not a constant.
because
So,
they're deteriorating as they're coming down.
well, not that, but they'd have to be coming through a much thicker section of the atmosphere if they were being detected horizontally. And so it's a Gaussian distribution with the angle, but that's,
And it's more likely to come down.
yeah, you get to get a stronger signal. Matthew first.
You said that it detects them at exactly the same time. It goes through both of them. But it goes through one and then the other. So how
Yeah.
can it be exactly the same time?
Because it's travelling at the speed of light, and the electronics that are processing it is it is several orders of magnitude less. And in fact, the software will count it as being at the same time if it's within 10 microseconds. But I think we're looking at picoseconds difference between the two. Noah,
What happens if it comes in like a diagonal icon, so basically the top one, not the bottom one?
it won't get counted. And there is, it only counts things that are within 135 degrees. So we plotted that out. Okay. And that's the answer to Lisa's question. That's the detector outside of its box. And the guts of the thing is a little block of silicon. And the block of, the big black block gives a little sparkle of light every time it sees a bit of radiation from whatever source, whatever species. And there's a photomultiplier that will produce an electric pulse when it sees a bit of light. I'll come to you in a minute, Hannah. That electric pulse goes through a couple of amplifiers and then a little microprocessor, and it's counted and displayed, and we can write it to a memory card. And that's how we actually get the data. Hannah.
How do you make one?
How do you make one? Well, basically, it's a design that was put together by some clever people in the physics department at MIT in America, big university in America. They made their design open source, which means anybody can look at the design and buy the bits and put it together. And that's what we've done. And the charitable enterprise that I'm a part of, we sell these, and we've sold 200 and we've built 230. And we're transferring production to China because the demand is so high. Bethany.
Is that why it says on like total count?
Yes. 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 And it's only been on for 2 minutes, yeah. And it's and this is counting all events. So the stuff we're interested in and the stuff we're not interested in. Okay, so let's have a look at some observations, shall we? So what can muons tell us about space? Now then, we're going to look at some graphs now. And some of you know all about graphs, and some of you, this might be something quite new. But basically, the picture we're looking at there, that data is from July last year up to December. And what do we notice about the orange colour? What do you think, Rex?
What colour is the muon?
Or what colour is a muon? Yeah, that is, I mean, the answer to that question is quite difficult. It's a really hard question. Okay, this is the orange colour, the red-orange colour here on the left, and it goes to the blue as we get to December. So what do we think that tells us?
The season effect on the muons.
And why do you think that would be? That is true.
It's because there's more radio waves coming from the sun.
Because?
It's hotter.
No.
Because it's closer to the Earth.
No. Oh, well, that's almost the case. Because?
Because when the Earth spins, only like one like side of the Earth is shown to the sun, and then that's where the muons come.
Yeah, I mean, you're both on exactly the right track, but the answer simpler. Bethany.
There's more sunshine.
Yeah, there's more sunshine in summer than winter. Exactly right. Yeah. That's it. beginning and end. There's more in the summer. Why? The days are longer, more sun. Okay, now then, this is a bit more difficult to see. And we've got to talk about, again, these are muons that are coming from the sun between January and December. So it's a whole year's worth. And the sun, we said at the very beginning, has sunspots and it chucks energy out into space. And it does this on an 11-year cycle. So it gets higher and then lower. And to do that whole thing, is 11 years. So we're only looking at an 11th of that here. But what can you, so the sunspots, so that's how active the sun is the bottom trace. And what can you notice about the bottom trace? Very gently, it's doing what? Bethany?
It goes more
Yes.
jaggedy.
Yeah, is that what you were going to say?
No, I was going to say that it goes like down a bit, like February-ish, and then it goes up.
Yeah.
So,
That is true, but the trend over the year is increasing. And if we count muons for a year, as this guy did, what's happening there? It's decreasing. It's decreasing. And this is to do with the Earth being a magnet and more muons being deflected into space rather than coming to the ground and being collected. Yes, decreasing. Okay, now we're back to this story. Do we remember this story? What happened? What happened in October last year?
Exploding star.
Yeah, exploding star. Here we can see more data, and it's quite difficult. Now, the star exploded in October, which is where the arrow is, and the data is showing us a day or two before to a day or two after. And can we see from this a change in the way the muons were detected? Hannah?
after the star exploded, is there like more muons?
Yes and no, and yes and no, and yes and no, and yes and no. You'll come to that in a minute. No. Can we see anything from that data? No. Well, I can because I know it's there, but it's very difficult to see. Now then, the good thing about data is that it can give up its secrets, and that's why math is so important, or mathematics for some of you. Okay? Now look, this is 12 hours before. The star explodes, and that's 12 hours after.
You said it was 2 to 3 days.
Yeah, I forgot. But we can see when the star explodes, we can now see, by processing the data, a different pattern of our muon count. So now we can see the change. So after the star explodes, we can see this on Earth with our very simple detectors, because this massive amount of energy from that exploding star makes the Earth's magnetic field oscillate. It's like a big jelly, and it goes boom, 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 boom. And so muons get squirted into space and free to get to sea level. And so we've noticed this pattern from that cosmic event. Okay, the star exploded, the Earth's magnet changes, some muons go back to space, and others. Now this is Jordan's story. Jordan is a third-year university student, really young man, and he thought he would do an experiment. He's at Lancaster University in physics department. He's studying physics, astrophysics, and he wanted to do an experiment. And it's the experiment that Bethany keeps talking about.
What experiment?
About muons being different at different heights.
Oh, yeah.
And so he thought, I'm going to put a detector in a sandwich box. And there's his sandwich box. Is it, what do we call it, picnic box? And then I'm going to get my friend and to help me, and we're going to put it on a balloon. And we're going to take the balloon up into space, and we're going to measure the muons and see what happens. That's your experiment, isn't it? That's what you wanted to do. And there it is. He put a camera on it, and you can just see the curve of the Earth. He sent a detector into space on the balloon and counted muons. Right. What can we see? This is data again. And this is the number of muons going up and down, and the height is going across. and it only goes to 7,000. And then his experiment stopped.
Because the balloon popped.
No. But basically, Bethany's idea about there being more muons as you go higher is absolutely right, and that's what the data shows us from here. And the experiment stopped for quite a sad reason, but it did work out for him. Okay, so what happens to muon when the balloon goes up? We've already noted it. Bethany predicted this at the beginning. Yeah, we count more muons. Right. What next?
Is that edited in?
24 or 25, we're hoping to put 2 detectors onto the ISS for a school physics project. And your school can join in. There is a school's physics project connected with the ISS, and we're hoping to join that project in next year or the year after.